Hello, everyone. Thank you for tuning in today for my presentation about analyzing ground movements induced by tunneling. I am Tatiana Risha, a first-year PhD student at Terrasol CETEC and École des Ponts Paris Tech. This thesis is supervised by Jean-Michel Pereira from École des Ponts and co-supervised by Gilles Chaperon at Terrasol. Today, I will present to you a small part of my thesis that works on the Grand Paris Express. So we'll have a closer look into the highlights of this huge project, and then I will introduce to you the EPB TBM, which is the Earth Pressure Balanced Tunnel Boring Machine. All of the railway is very well instrumented in order to have every data about the TBM and about the ground movements. We will see together what are the main parameters that are saved, how to clean this data, and some ways of analyzing it. Grand Paris Express is the largest transport project in Europe with 200 kilometers of new railway lines that are fully automated. It has to be noted that all of this metro system is excavated in a very dense urbanized area. Therefore, it is very important to have a proper estimation of ground movements to avoid risks. In my thesis, thanks to CETEC, I have access to all kind of information on line 14 South and 15 Southwest. Altogether, they form about 22 kilometers of new, very well instrumented area. Up until now, I've put all of my focus on line 15 Southwest. So here it is, a closer look into it. It is divided into three parts. TR1, it was the first one to be excavated. Then TR2 followed, and the excavation of TR3 has just begun using the TBM of TR1. So we just need to keep in mind that TR1, TR2, and TR3 are three parts of this line, and each of this part is divided into smaller sections. Like here, we can see that TR1 is divided into TR1A, TR1B, up until TR1H, and so on for TR2 and TR3. As I already mentioned, these lines are excavated using big cylindrical machines called the TBM. The Society of Grand Paris worked with Herrenknecht, it is a very known construction tunnels manufacturer, to get the specific type of TBM, which is the EPB. In this image, we have an EPB, of course, and let's see how it works. The cutting wheel here is responsible for cutting the ground with the help of many disc cutters. All of the soil gets into the excavation chamber where it will be mixed with the polymers in order to have some sort of paste that can easily be taken out by the screw conveyor. And the screw will take the paste up to the top where it will be put on a moving carpet all the way to outside of the tunnel. The tunnel lining right here, it forms what we call a ring. Here we need the 7 segments to form that ring. The segments are installed into place with the help of the erector that works like a suction cup. The TBM moves forward thanks to the help of the hydraulic jacks that push on the ring itself. And one last thing is the tail skin. Its length is about 14 meters and it's tapered. Not much, but for scale, the diameter on the front is about 9.87 meters, whereas the diameter at the end of the tail skin is 9.8 meters to be exact. Here's a closer look on the cutting wheel. This is the TBM that excavated the TR2 of line 15 Southwest. It just finished 2 weeks ago on the station of Villejuif-Louis-Aragon. Let's go back to our main subject, which is crown movements. How does tunneling with the TBM affect the crowns? First, there's face extrusion. The crowns have a tendency to move towards the opening. Second, there's the convergence. And as we know, once excavated, the ground will tend to converge. Special attention should be taken in order not to jam the tail skin, and overcutting, bad guidance of the TBM are factors of ground movements as well. Third, the tail gap. Since the segments are posed inside the tail skin, there is a gap between the segments and the tail skin called tail gap. This one is filled with grout, And in case of bad filling, it can be a source of crown movements. Fourth, the lining deformation. That can occur, for example, because of the thrust applied by the hydraulic jacks on the ring. And fifth, finally, the consolidation. Some types of encountered soils may consolidate sometime after the tunnel has been excavated. In order to avoid the ground movements and to foresee risks, lots of monitors have been implemented on the surface as well as underground. CAP, which is a subsidiary company of Vinci and SPI Batignolles, was responsible of providing the data related to the TBM machine, which are phase pressure, grouting pressure, penetration rates, etc. We have hundreds of parameters. Targets were installed as well by Sixth Sense, which is another subsidiary company of Vinci. They were displayed on a platform named Geoscope. Thanks to these targets, we have access to data of ground movements, whether the vertical movements and the horizontal ones. Let's begin with TBM operating data that are provided by CAP. The data is given in forms of images on a dedicated platform. We have many types of reports, and for each type, we have a report for every ring installed. So, for example, for the installment of ring 10, one can go into the platform, open the report number 10. He will find inside of it the information about the TBM while excavating and posing ring 10. Monitoring data are published on a web platform as well. Targets on the surface measure vertical movements. They can be installed on roadways or buildings. It is to be noted that measures taken by targets on buildings are affected by the building's stiffness. Therefore, in the first approach of analyzing data, I only worked with data taken by targets on roadways and virtual targets. We also have extensometers, inclinometers, and others. In order to analyze all of this data, I personally chose to work with R language on RStudio. This language is recommended for statistical computing and graphics. It is very easy to use and to learn, especially for people that don't have lots of programming skills. Our language has a very big community online, so we can easily find answers to encountered problems while coding. It contains lots of libraries. I cited here a few of the ones I found interesting for my work, like Arvest to connect to web, Magic that does image treatment, Lubridate for handling dates. Tidyverse is a collection of many packages. It handles tables and graphs, and Data Table is a very powerful library to work with tables. Back to TBM operating data. As I said, the data is on images on the web. Therefore, as a step one, I had to do some web scraping to extract those images automatically. So all I have to do is to create a session, give the link of the image, the log infos, and after that, we can open the image link, extract its content, read the image with the Magic library, and finally save it on my personal PC. As a step two, I had to make a code that will read specific characters in the image so I can save the info in a data table. So I gave it the digits that might be present in my text. That way, the error is reduced a lot. I did some image enhancing, and finally, I called the built-in OCR function. For those of you who don't know, OCR is an abbreviation of optical character recognition, which converts images of text into typed text. I had to do separate functions for dates, durations, hours, because the output is of different type. Well, you might wonder why the data isn't already given in data tables by CAP. In fact, CAP gives a table as an output, but it doesn't contain all the data that's in the images. So it wasn't sufficient for my future studies in this thesis. The last step was what we call data cleansing. It's the process of cleaning data. In my data table output, I had data that was duplicated, so I did a deduplication. There was missing data, so I had to handle it. I checked the quality of the OCR, which, by the way, was very good, like 99.7 or 8% of my values were correct. And unfortunately, some of the data was wrong, originally wrong in the CAP database. So I had to correct it. And finally, as I already told you, there are many reports. So I merged all of the infos extracted from all the type of reports together in order to have one big final table containing TBM operating data. Finally, the database will look something like that at the end. Here's just the 5 first columns. There are lots more behind containing the TBM operating data like pressures, rate of advancement, etc. And voilà, this is what we call a TD data, which means that it's clean and organized in the best way possible. We can see 4 lines for each ring. PM RDC as root coup is the metric point of the cutting wheel. PM here is the metric position, excuse me. It's the metric position of the ring. We can notice that there's 12 meters between the two, since the ring is always posed 12 meters behind the cutting wheel. We also have a column for the phase. So each ring passes through 4 stages. That's why we have 4 lines for each ring. The phases are beginning of excavation, ending of excavation, beginning of posing the ring, and the end of it. And each phase, we have its exact date and time for it. With such a database, we can easily plot graphs like this one, which shows the advancement of the tunnel through time. Here we have the metric point of the ring versus the date, and we have the numéro anneau, which is the ring number. I save these files as HTML files. So just usually if we open it as an HTML file, just by moving the mouse on a point in the plot, we can have the exact value of each point. Another form of the graph would be the ring number versus the date, adding the phase. This is also an HTML file. We can as well plot any TBM parameter versus date or cutting wheel or whatever we want. Here, for example, I made a plot of volume of crowd injected in the tail void versus the cutting wheel position, and phase pressure versus the cutting wheel position. Let's move on to soil monitoring data. The web platform wasn't as simple, so I had to ask for the help of an expert in web scraping at CETEC. He chose to do his code on Python and worked on functions, loops to extract all the data in all the layer in Geoscope. Okay, layer, if you remember here, when I showed you the Geoscope, the layers were all of these, so containing the targets on roadways, on buildings, the extensometers, tiltmeters, etc. The output of his code was 2 Excel files for each section division. Okay, in the first one, called résultat as in results, the first column indicates the date and time, and the rest of the columns are the targets. So we have one column per target, and the values inside are the settlements saved by this target, measured by this target. The second file, called entities, contains information about the target. And by information, I mean its ID, its coordinates, name, layer name, etc. And knowing the layer name, we know now the type of the target and its place, whether it's on roadways, on buildings, and so on. As mentioned, we have now the coordinates of the target. And since we already have the coordinates of the tunnel line, we can draw nice maps that show us the position of the targets and the settlements they measure. Here, I chose to only show you the targets on roadways and virtual targets. It's a personal choice. And it was the first trial. So I chose a random date and showed the settlements measured by the targets on this specific date. Now, we have data about the TBM and data measured by targets. The TBM data gives us the date and the cutting wheel position. If we look onto one target data, what does it give us? It gives us the date of the measure and of the measure of settlement and the target position. By merging the two tables together by date, we get an important information, which is the distance to face. What's the distance to face? It's the distance of the target to the face of the tunnel for each settlement measured. So finally, here's the data table after merging these two tables. We have the first column is the section where the target is implemented, the ID of the target, its name, coordinates, type, its position relative to the tunnel axis. And by dx, I made a small image here, a small drawing here about the tunnel axis and the target. The perpendicular distance between the target and the tunnel line is the d-axis. And finally, we have this information here, the date, the distance to face, and the settlement. Well, if we take all of the targets together, we're going to have a very big table with about 26 million something rows, which means it's 3.6 gigabytes. Whereas if we only filter it to have only the virtual targets and targets on the roadway, we're going to have a table with 5 million something rows. So it's reduced to 0.7 gigabytes. You should know that the analysis on these data is a work in progress in my thesis. So we're going to see now how I filtered the data and the plots that can be deducted. The next step would be removing outliers. How can we do so? First thing, for each target, I calculated the quantile for settlements at 0.1 for Q1 and 0.9 for Q3. And by 0.1, 0.9, it means that it's 10% and 90% probability. I then calculated the interquantile, which is Q3 minus Q1, and I removed the outliers. An outlier is a value that's below Q1 minus 1.5 interquantile or above Q3 plus 1.5 interquantile. As you see, I did my calculation on every target alone, not on all targets in a section, because I remind you that every target has a different distance to the tunnel axis. And as we know, data right next to the tunnel axis won't measure the same targets right next to the tunnel axis, won't measure the same values as targets 50 meters from the tunnel axis. Let's take a closer look into the number of measures removed with this method. We have a plot for each section. Here I chose to show you the TR2B. It contains all the targets in this specific section. On the y-axis, we have the number of removed data, and on the x-axis, we have what I call the sector, which is the distance to face of the tunnel when the settlement measure was taken. We can see different colors on the plot, which each one represents a different target in the section. We see that most values removed are very far from the face of the tunnel, like 50 meters before the TBM passed by, or more than 70 meters after the TBM passed by, and passed by the target, I mean. The proportion of the removed data doesn't exceed 1.5% of all the data measured by the target. So it seems like it's okay, and there's no problem with that, except for some cases because we have bad targets that give us wrong values. There. Now, once the outliers are removed, I plotted the density of the settlements. Notice that I only took targets that are 10 meters far from the tunnel axis. TR1F is a typical case of settlement distribution. This plot is divided into small plots, each one for a specific distance to face range. For example, if we look at the plot in the middle, which show measurements taken between 5 meters before the TBM passed by and 60 meters after, we can see that the settlements are mostly between 2 and nearly 3 millimeters. Whereas 40 meters after the tunnel passed by, the settlements are stabilized at about 4 millimeters. Having all of this clean data allows us to plot settlements versus date and distance to face. Like the plots before, this one is also an HTML file. Another way to plot the same information would be to plot distance to face and settlements versus the date. And we can as well find a series of targets aligned that cut perpendicularly the tunnel line. We get their settlement measures and plot the stabilized settlement that was measured. We then plot that value versus the distance to axis of the target. And we get the famous settlement trough that follows a Gaussian distribution. Here's just two examples, and I remind you this is a work in progress in order to automate the process. As a conclusion, it is very important to analyze ground movements to avoid risks. Therefore, installing instrumentation and analyzing their data is crucial. Data extraction and cleansing is a long process, but it is unavoidable to have a good analysis. Merging TBM operating data and soil monitoring data allows a better reading of settlements, considering all the TBM parameters. As perspectives, more advanced statistical analysis should be performed on the settlements data. Thank you so much for your attention.